Darn it, Euclid, why doesn't this thing work? No editorial comments, thank you.
Oh, hi, Christine. What are you doing?
Hi, Kanwal. I'm trying to fix this camera. What's in the bag?
Chips.
Math chips?
No, these are sour cream and onion.
Oh, my favorite kind. Hi, you're watching The Math Shop, the program where real math meets real life and triumphs every time. I'm Christine, and this is my partner, ace math coach Kanwal.
Hello.
And this pile of gear over here is my homemade, usually brilliant computer, Euclid. Today, we investigate factoring, what it is and how to do it. And we conclude with the solving of rational equations and other equations with fractions in them. Which reminds me, I got a call from Conchita, my cousin, the other day, and we've got a great problem to work on.
Oh, tell me about it.
Okay, well, actually, I got some footage, so I'll just let Euclid roll it. Euclid, clip 1, please. Conchita is an amateur photographer, and she just got a job with the Freudian Slope Image Bank working on a multimedia installation. She makes enlargements of photos and then digitizes them so that they can be manipulated on the computer. The problem is the first set of photos she made weren't big enough. The computer needed more information for the digitizing. So her boss told her to double the image size.
That sounds simple.
Yeah, it does. But, you know, when she doubled the size of the prints, her boss still wasn't satisfied. The new photos were taking forever to digitize and eating up way too much computer memory. He said she made them the wrong size.
I think I understand. How big were the first photos?
4 by 6. Euclid?
I see. And the new photos?
Well, she doubled the size so they were 8 by 12.
Yes. I think I know what went wrong. She doubled the dimensions, but she needed to double the area. This really is a good problem for us because it can be solved by factoring. Let's get down to work. Factoring simply means taking an amount and rewriting that amount as a multiplication problem. Or, to put it in another way, finding factors which, when multiplied together, will produce that amount. Suppose that I have the amount 6. I can rewrite that amount as 2 times 3. And that is a very simple example of factoring.
It's important to remember that, like this cable, which can carry a signal in either direction, the process Kanwal just showed is a two-way street. The opposite of factoring is called expansion. Let me demonstrate. Euclid? If I start with 3x plus 9 and factor it, I get 3 times x plus 3 as a result. If I expand 3 times x plus 3, I get 3x plus 9 as a result. Let's look at another more complicated example. The principle is the same. If I factor 6m squared n plus 4mn squared minus 8mn, I get 2mn times 3m plus 2n minus 4. Likewise, if I work backwards and expand, you can see that I get the same expression I started with. There are a number of methods used to find common factors. One is to use the distributive property, and another is to factor by grouping.
Just to remind you, the distributive property works like this. For any numbers, well, let's call them A, B, and C. A times bracket B plus C bracket is equal to AB plus AC. Similarly, for any numbers A, B, and C, A times bracket B minus C bracket is equal to AB minus AC. Let's look at an example. Euclid? 4 is a common factor in each of these terms. Therefore, I can put 4 outside the brackets and put the original expression divided by 4 inside. In the same way, because x is a common factor, I can put x outside the brackets and divide the expression inside them by x. So, the greatest common factor is 4x. Remember, this does not change the value of the expression. It is just another way of writing the same thing.
But Kanwal, haven't you forgotten about Conchita's problem?
No, not at all. But we need to go over a few more of the basics of factoring before we can do her problem.
So you mean that in solving Conchita's problem, factoring will become a major factor? Thank you. Thank you very much.
I couldn't have said it better myself. Now, another way of finding common factors is grouping. Suppose that I have this expression to factor: 3gh plus gb plus 6ah plus 2ab. By inspection, I can see that two of these terms contain a g, and two of these contain an a. If I group these terms together, and I group these two terms together, I have two binomials which can be factored. A common factor in the first binomial is g, so I factor that out. I have 3h plus b. And a common factor in the second binomial is 2a. So I factor that out, and I have 3h plus b. Now, notice that the two binomials in the parentheses are the same, 3h plus b and 3h plus b. Now, how many 3h plus b's do we have? Well, we have g plus 2a of 3h plus b. And according to the distributive law, this is the same as this. And these are the factors of the expression we started with.
Well, at least I'm getting an image now. There certainly is a difference in squares. Which happens to be the next method of factoring? The difference of squares. Euclid, some binomials, please. You will sometimes be asked to factor binomials which consist of one perfect square, such as 4, or 25 subtracted from another perfect square, such as x squared or y squared, or in other words, a difference of squares. Mathematically, every number has a square root, but perfect squares, and we're not talking dweebs here, have a square root which is a whole number. You can factor binomials which are a difference of perfect squares quite easily. Watch. Kanwal?
Suppose I have this difference of squares to factor, 9x squared minus 16. Now, each term is a perfect square. The root of 9x squared is 3x, and the root of 16 is 4. But to obtain negative 16, there has to be a difference of signs. The factors, therefore, are 3x plus 4 and 3x minus 4. This follows the standard form of factoring a difference of squares, which is a squared minus b squared is equal to a plus b and a minus b. Let's try this with another example. 25m squared minus 9. I know from the standard form that the difference of perfect squares will look like this, with a plus and a minus. The root of 25m squared is 5m, put 5m and 5m, and the root of 9 is 3. So the factors of 25m squared minus 9 are 5m plus 3 and 5m minus 3.
Don't forget to check your result. Oh, why don't you use the FOIL method? Remember, the FOIL method is a way of expanding binomials, and it gets its name from the initials F-O-I-L. First, outside, inside, and last.
Let's use FOIL to see if this method of factoring actually works. Let's check this one. If we multiply the first term by the first term, we multiply 3x by 3x and get 9x squared. Next, I multiply the outside terms, multiply 3x by negative 4, which is negative 12x. Next, I multiply the inside terms, 4 by 3x, and I get 12x. And finally, the last terms. Positive 4 times negative 4, which is negative 16. When I look at these terms, I see negative 12x and positive 12x cancel each other out, which gives me the original expression 9x squared minus 16. Therefore, my factoring is correct. But remember, this works for the difference of squares, not for the sum of squares. The sum of squares cannot be factored. Let me show you why. Four x squared plus 1 is a sum of squares, not a difference. Both are perfect squares. The root of 4x squared is 2x, and the root of 1 is 1. But if I try to find binomial factors, here are my possibilities. 2x plus 1 times 2x minus 1. Another one is 2x minus 1 times 2x minus 1. And the third one is 2x plus 1 times 2x plus 1. Now, the first possibility will give me 4x squared minus 1. The second will give me 4x squared minus 4x plus 1. And the third possibility will give me 4x squared plus 4x plus 1. But none of these is the sum of squares I was looking for. So you can see when there are two terms which are perfect squares that are added together, you cannot factor the expression.
You probably know that this is called a tripod because it has 3 feet. Tri means 3 and pod means foot. In mathematics, an expression with 3 terms in it is called a trinomial. And certain trinomials can be factored if they're in the right form. Euclid, a trinomial, please. If the coefficient of the squared term is equal to 1, as in this case, it's factored differently from a trinomial in which the coefficient of the squared term is not equal to 1. As in this example, 8x squared plus 14x plus 5. Let's begin with a trinomial in which the coefficient of the squared term is equal to 1. Euclid, could we see that example again, please? We'll use a technique called the sum and product method. I know that the factors of y squared will be y, so I'll concentrate on the numeric portion of the expression. I need to find 2 integers that have a product of 12 and a sum of 7. Now Euclid has given us factors of 12, such as 1 and 12, 2 and 6, and 3 and 4. But only one pair has both a product of 12 and a sum of 7. That's the last pair. Therefore, the factors of this expression will be y plus 3 and y plus 4.
Now, let's do another example. And remember, we're working on factoring trinomials that have a square term with a coefficient of 1. Euclid? Again, I look at the integers in the expression and see that I have to find factors of negative 45 that have a sum of negative 4. And I see from the table that the factors which meet these requirements are 5 and negative 9. Therefore, the 2 factors of this trinomial are y plus 5 and y minus 9. There's just one more method of factoring that we will look at today. It is a little more complicated. It involves a 7-step process. But we work with all of the steps in other methods. So it is just a question of putting the pieces together. Euclid, one more example, please. Remember, in this case, we are factoring a trinomial in which the coefficient of the square term is not equal to 1. Step 1 is to multiply the first coefficient by the last number in the trinomial, which in this case gives me the number 40. Step 2 is to list all the possible factors of the product from step 1. In step 3, I select the pair of factors which, when added together, will give me the number of x's in the second term. Now, in step 4, I rewrite the expression using the two factors I just found in the table to make a 4-term expression instead of a 3-term expression. In other words, I replace 14x with 4x plus 10x. In step 5, I separate the first two terms and the last two terms to make two groups. In step 6, I take the largest common factor out of each pair of terms. In the first group, that is 4x, and in the second group, the largest common factor is 5. And now, I see that the terms inside the parentheses are the same, so this allows me to use the distributive law to rewrite the expression this way, which is step 7. If I multiply these out, you will see that these produce our original trinomial, so our factoring is correct. And now, Christine, we are ready to look at your cousin's problem. She made some photos 4 by 6, but they were too small. She was asked to double them, so she printed the photos 8 by 12. Well, the first part of the problem is that Conchita's boss didn't define his terms clearly enough. He said double the size of the prints, so she doubled the length and the width. But when you scan a photo, you are scanning the area. So what he probably meant was double the area of the print, okay? The double area will be 2 times 4 by 6, or 2 times 24, which is 48. There are a number of different ways of doing that. I'll show you one way. Suppose I double the area of this photo by adding an equal amount, let's call it r, to both sides of the length, r, and both sides of the width, r. So my resulting equation could look like this: 4 plus r plus r for the width, and 6 plus r plus r for the length, which is equal to double the area of 48. Now, we can solve using the techniques we've been practicing. We can rewrite the terms on the left as 4 plus 2r times 6 plus 2r is equal to 48. Next, I can expand these two binomials using the FOIL method, which gives me first times first, 24, plus outside 8r, plus inside 12r, plus last 4r squared, which is equal to 48. Now, I can add the 8r and the 12r, giving me 24 plus 20r plus 4r squared equals 48. And then I'll rearrange the expression so it is in the proper order. 4r squared plus 20r plus 24 is equal to 48. Next, I subtract 48 from both sides of the equation. I have 4r squared plus 20r minus 24 is equal to 0. And now I would like to change my expression so it has a coefficient of 1 for the square term. This will make it easier to work with. So I divide both sides of the equation by 4. This gives me 4 divided by 4, r squared, plus 20 divided by 4, 5r, minus 24 divided by 4, 6, is equal to 0. And now I have r squared plus 5r minus 6 equals 0, and this is something I can factor. Since the coefficient of the square term is equal to 1, I look for factors of the last term whose sum is equal to the second term. In this case, positive 6 and negative 1. I have r plus 6 r minus 1 equals 0. Now I have two binomials whose product is equal to 0, which means that one or the other of the binomials must equal 0. Therefore, here r must equal -6, and in this case, r must equal 1. Since we can't have a negative value for r in our problem, then r must be 1. Let's go back and substitute into our earlier equation and determine the dimensions of the enlarged photo. Well, r is 1, and 1 here, here, and here. The result is verified. 6 times 8 is 48. And that is also our new dimension, 6 by 8.
So, Conchita, if you're watching, you should make your enlargement 6 by 8. That will double the area. Hello, Math Shop. Oh, hi, Conchita. Yeah. Well, we're right in the middle of a show. Oh, an emergency. Oh, okay, okay.
While Christine takes that call, maybe Euclid and I can review what we've learned about factoring. Once you categorize the type of expression you're trying to factor, you can apply one of the following methods. Euclid?
Conchita, are you sure?
First of all, always look for a common factor. Then factor out the greatest common factor. Next, look at the number of terms in the expression. If there are two terms, try factoring it as a difference of squares. But remember, don't bother trying to factor a sum of squares, because it won't work. If there are three terms, look at the coefficient of the squared term. If it is equal to 1, then use the sum and product method. If it is not equal to 1, then use the 7-step approach we outlined earlier.
But that's not enough time.
As we said earlier, a rational equation is one which involves rational terms or fractions such as this. 2/3 minus 5/6 is equal to 1 over x. It is an equation in which there is a variable in the denominator. Okay, Euclid, an example, please. Thank you. Here is a rational equation, and my first step is to clear the equation of fractions. Note that x is equal to x over 1, and 5 is equal to 5 over 1. Therefore, I can rewrite the equation in this form. X over 1 plus 6 over x is equal to 5 over 1. Now, I multiply both sides of the equation by the lowest common multiple, which is x. This will eliminate the fractions. Watch. I am left with x squared plus 6 equals 5x. And now I can carry out the usual equation solving process. First, I subtract 5x from both sides of the equation, giving me something I can factor on the left side, and 0 on the right. This is called the standard form of the equation. To get the answer of 0, one of the two expressions must equal 0. That x is either 3 in the first bracket or x is equal to 2 in the second bracket. And using these values, I go back to the equation and check. And I find that both solutions are correct. The solutions are 2 and 3.
I'll figure out something. Bye.
Now we should try to apply this to a problem.
Kanwal, this is a real emergency. We have to stop. Conchita's in big trouble.
So we're in the middle of a show
yeah,
right
I know.
now.
It doesn't matter, though. We have to stop. Conchita's in trouble and the clock is running. I'm sorry. And besides, Kanwal, I promise you that this problem will give us an equation that has a fraction in it.
Okay, well, what is the problem?
Here's the deal. Conchita just got to work and she found out that she has to scan 100 photos by the end of today so that they can be put on a plane to Vienna. Okay, that gives her 8 hours, right? Now, with her equipment, she can do one picture in 10 minutes. I offered her Euclid, and I think I got all the video bugs worked out of him, and he can do one picture in 6 minutes. Now, the question is, can she get it done, and if so, how?
So let's do it with a table. One column can show us the time per photo.
Right.
The next column can show us the number of photos. And the last column can show us the total time taken.
Right.
Okay. So let's fill the table for Conchita and Euclid.
Okay, well, it takes
Okay.
Conchita 10 minutes for each photo.
Okay.
And there are 100 photos.
All right.
So that means 1,000 minutes.
Huh?
And 1,000 divided by 60 minutes equals 16 2/3 hours.
Okay.
Right?
Yeah.
Too long.
Yeah,
Euclid
that's
can
right.
do it way faster, okay?
Okay.
It takes Euclid 6 minutes per photo.
And still 100 photos.
Right, right. So he'd be able to do all of that in 10 hours.
Okay.
Still too long, you know.
Yeah.
So I don't think either of them can get this done alone.
That's true. Now, what did our poster say about this?
Strategy. Think about a strategy. Okay, well, what if they work together?
All right. Conchita can do half the photos, let's say, in 8 1/3 hour. Oops. And Euclid can do half of those in 5 hours.
Still too long.
That's still too long.
Well, let's try looking at the problem from another angle. Let's let the number 1 represent the entire job. Using both machines, how much work can be done in a minute? Euclid, could you help us out, please?
Ah, good. This is a table of the amount of work that can be done every minute. In 1 minute, Euclid can do 1/600th of the required work. Conchita can do 1/1000th of the required work. Working together, they can do the sum of those two fractions, which, when we convert to a common denominator, works out to be 8/3000ths of the work.
In 2 minutes, they can double their output. So the pattern is clear. If we allow the entire job to be represented by the number 1, we can construct an equation to find the shortest amount of time required to complete this job.
The equation is T over 600 plus T over 1000 equals 1.
And you can use some of the techniques for solving rational equations on problems of this type as well.
And what do we do? Well, first of all, we need to find the lowest common multiple. In this case, the lowest common multiple of 600 and 1000 is 3000. So I rewrite the equation to obtain a denominator of 3000. I multiply the top and the bottom here by 5, the top and the bottom here by 3, and the top and the bottom here by 3000. When I multiply through, the equation now looks like this. 5t over 3000 plus 3t over 3000 is equal to 3000 over 3000. And now I want to convert these fractions to whole values. So I multiply the equation by 3000 to eliminate the denominator. And I get 5t plus 3t is equal to 3000. And now I collect the like terms. I have 8t is equal to 3000. I divide both sides by 8 and find that t is equal to 375, which is minutes. And if I divide by 60, I find this is 6.25 hours, or 6 hours and 15 minutes. Yes, the job can be done in under 8 hours.
Oh, great. Okay, Conchita, I'll be there right after the show. That's it. That's the end of the show.
And we're out of here.
That's right. So tune in next time to the Math Shop.
Goodbye.